In this case, we're talking about solutions. Chapter 4, Section 4 was all about solutions. So I want to go into this a little bit more and talk about aqueous solutions. And we talk about how things are dissolving in water. So we say that if something's aqueous, it's when your solvent is dissolved in water, right? Well, some compounds dissolve in water, and we would say that they dissolve in water well, but we're basically going to talk about whether they dissolve in water or not, okay? I admit there's some middle ground here, but for now, it's important, I think, for you to first appreciate what it means when things dissolve in water, okay? And ultimately, of course, we're going to go, wait a second, some things don't dissolve in water? Really? Is that true? And if that's the case, then what's that mean to us as students? Okay, so first of all, let's talk about a water molecule. So this is a water molecule, or a space-filling diagram of a water molecule. This is essentially like the area that electrons occupy, where this is the oxygen atom. Can you see red there? And this is a hydrogen atom. This is a hydrogen atom, okay? And there's a covalent bond and a covalent bond. So this is the nucleus of the oxygen atom and hydrogen. Well, the electrons are all racing around here, right? Well, it turns out the oxygen gets more than its fair share of the electrons because it's electronegative. And that's a term we won't get into until chapter 8. But suffice it to say for now that an electronegative element is one that hogs the bonding electrons, okay? So if hydrogen's got, there's sort of 2 electrons that are composing that bond right there, they're really getting pulled in this direction, and that leaves a partial minus charge here. It's not an ion, but it's got a partial minus charge. Its charge is not exactly balanced, okay? And if it's got a partial minus here at this end, it's going to leave sort of a scarcity or paucity of electrons on this hydrogen nucleus, and so we'd say there'd be a partial positive here and a partial positive here, okay? So water, then, what we'd say is polar, and that's what makes it polar. We get definitely way deeper into polarity in chapters 8 and 9. But I want to, first of all, look at a water molecule and say, all right, this is one reason why it's such a good solvent. It's not ionic, but it is polar. All right, so let's now look at sodium and chloride. So if you get sodium and chloride, if you have a sodium chloride lattice, which we've got a couple pictures coming up here of a sodium chloride lattice, you might have like a sodium, chloride, 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 sodium, 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 right? You get this that's a chloride actually. Here's another chloride. Here's a sodium, right? So you get this lattice. It's basically like piling a bunch of boxes on top of each other of sodiums and chlorides, right? Well, that's if it's a solid. Okay? Well, now, in order for it to dissolve, then our solvent interactions and our solute interactions have got to, the solvent-solute interactions got to be important, big, okay? And the solute-solute interactions has got to be overcome by this one, right? So when we're dissolving means this interaction, which I'll call interaction 1, wins over interaction 2. And the chlorides then will all get surrounded by water molecules, okay? Now, can you see from the previous picture, here's sort of a smaller version of the previous picture we had a previous slide. You've got some partial positives here. Can you see how the partial positives can mask a minus and a positive, right? The 2 positives, they're not real full positives, they're partial positives. But they can sort of go all over this chlorine ion, and it turns out that's what they can do. They can make a blanket. It's called a hydration shell. Well, on this side, we have the partial minus. And look at that partial minus. That can go, if I can draw that like a V, I was doing that here. There's my V here, right? Draw that like a V. Then the minuses can all make a hydration shell on top of a sodium ion also, all right? And so that's how sodium chloride is dissolved. Now, let's look at that. Let's look at that picture in more detail. here's my sodium chloride lattice, which I drew in the previous slide. My sodium chloride lattice, and each one of those chloride ions is getting sort of touched, right, by those partial positives. Those are the hydrogen atoms. Can you see that from where you're sitting? Is that too small? Those all have partial positives on them, and they're making a blanket around that chloride ion. And the same thing goes for the sodium ion. It's getting a blanket, but in this case, it's the minus on the oxygen, the partial minus, which is touching that positive ion, right? And that's why sodium chloride dissolves in water. Okay, so let's look at another picture of that. Suppose that you've got, here's your lattice again. Suppose you've got 4 formula units in there. That would be 1 sodium and 1 chloride would make 1, how do you spell formula? Formula unit, right? Because it's a sodium and a chloride. Well, if you've got 4 of those in there, I mean, in this box, it's can you see there's 4? 1, 2, 3, and 4. Okay, when those get dissolved in water, now you've got 8 ions, right? Can you see that? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and that'll have some importance when we talk about its conductivity, how conductive something is. So anyway, we've got these a bunch of little ions in there. This is a minus, and there's a plus, and a minus, another plus. All those ions help conduct electricity, and that's what we mean by conductance. All right, so let's keep going. Oh, here's another picture of I probably should have put this in a different order. Here's another picture of a solution. We're still talking about solutions, right? This probably belongs someplace else. But here's a gas solution, right? Can you see nitrogen, N2? If each blue sphere is a nitrogen atom, then here's a nitrogen molecule, a diatomic molecule of nitrogen gas, right? Well, in this case, we've got a gas, and this definitely belongs in a different sequence. But here's a gas solution. Which is the solvent? Which is the solute? I'm not even going to answer that. I'm going to let you guys answer that. It may show up in a quiz. That'd be a good quiz question. I don't always remember to ask those, but that would be a great quiz question. If showing you this picture, which is the solvent and which is the solute? Okay, I'm fighting the temptation to answer it right now. Okay, so let's consider more. If we have sodium chloride dissolved in water, sodium chloride dissolves very nicely in water. It's soluble, dissolves very nicely, and it dissolves in ions. And so that makes something called an electrolyte solution. An electrolyte solution is something that conducts electricity. Okay? And it conducts electricity because it's got all these ions in it, pluses and minuses. I've got a ton of slides here like this, and I'm sort of, okay, yeah, this is what I mean by it. It conducts electricity. So if we take salt in here, now what you've got in that bucket, if we're dissolving salt in there, is we've got a bunch of pluses and minuses, right? Minus, plus, minus, plus. You can't see them, of course, they're too small. Minus, minus, minus. But that is going to take the electrons from one electrode to the other very nicely, complete the circuit, and it's going to make the light bulb glow. All right, that conducts electricity. Now, if you put sugar in there, even though the sugar dissolves very nicely, it will not conduct electricity, right? And you're still going to get some glow here if you do that, but that's only because the water itself is ionizing. You're going to get some H pluses in there and some O minuses. Not many, but some. But it's not the sugar that's conducting electricity. We would call this non-conductive. That's because when you dissolve sugar, it does not break up into ions. Does not break up into ions. And you might say, what? What are you talking about? All right, so we've got a picture here of how sugar does break up. So a sucrose molecule, it's a little bit busy. It's a little hard for you to see. Each one of these blacks is a carbon. Each one of these blacks represents a carbon. Okay? And sucrose is C12H I don't remember, 22O11, I think, something like that. It's real close to that. So sucrose has got a bunch of carbons and a bunch of hydrogens and a bunch of oxygens in it. Each one of these white spheres represents a hydrogen atom. Okay? What happens is you have, in sucrose, you have all these oxygens. It turns out these oxygens make an electrostatic interaction. It's a solvent, let's see, a solute-solvent interaction, right? Each of these hydrogens is going to be interacting with an oxygen. Each one of these hydrogens is going to be interacting with an oxygen, right? Can you see that? Here's an oxygen and a hydrogen, and they're interacting with something called hydrogen bonding. It's not really a bond, it's an electrostatic interaction. Hydrogen bonding. But, and it's important to appreciate now, this sucrose molecule does not break up into ions. It just gets surrounded by water, and it says, all right, yeah, this is fine. This is great. I like it better than hanging out with other sucrose molecules. Okay, so the interaction between sugar and water molecules is shown here, but it's, again, does not break up into ions, so this will not be conductive. Not conductive. Not electrolytic. Okay, it's a non-electrolyte. Let's look at another one now. Oh yeah, so here's the picture of it. A non-electrolyte solution, and it's because you've got these sugar molecules which are hydrated by water. There's a bunch of water molecules around them. You can't see them. Of course, these are not drawn to scale, right? They'd be way, way, way smaller than you could see with a microscope. But it's important to appreciate that they are not in ions. You actually have these full molecules which are floating around. They do not conduct electricity. They are not electrolytic. Okay, why? No ions. Okay, so now the next type of electrolyte, I should have warmed you up for this one, is acids. So we talked about definitions of an acid in chapter 3, but a strong acid is going to conduct electricity and a weak acid will not or won't do it well. And let me remind you what the definition of an acid was. You've got some component here with an ionizable hydrogen, and that is going to leave the electrons behind, and it's going to make a free hydrogen ion, right? Hydrogen ion. Okay. Now, if you have a strong acid, that means this reaction is going to go to completion. So every molecule is going to break up into those. So lots of ions. Lots of ions. Can you see ions here? Okay. Now, if you have a weak acid, that means that you've got some, and it goes in, we would call it equilibrium. And this does not go much forward. How do you spell forward? Let's pretend that's a W, okay? This does not go much forward. In other words, most of the stuff mostly stays as a H because it's a weak acid. It doesn't donate the protons well, okay? Not many ions. So if you don't have a lot of ions, you're not going to conduct electricity well, okay? So a strong acid, I think our next picture then shows a strong acid is going to, the example it's given is HCl. Strong acid is going to have lots of ions in it, a bunch of H pluses, and a bunch of Cl minuses. And this is going to conduct electricity. This is going to be very conductive. Okay? By the way, you might say, how am I going to know if it's a strong acid or not? That's something we need to cross that bridge a little bit later. Let me tell you, HCl is a strong acid. HBr is a strong acid. And H2SO4 is a strong acid, sulfuric acid, okay? So these are some strong acids, and that means they're going to conduct electricity because they're going to lose their H pluses, right? It's going to make a bunch of ions in the solution. So that's conductive. And then we'll give you the full list of strong acids later. For now, let that be enough. Okay? Now, a weak acid, acetic acid, C2H3O2. We've already seen this in class. Okay, so this is acetic acid, vinegar, and this is not going to make up you see most of these guys are intact, okay, but a few of them will lose their H plus ions, and so we'll have few ions, so we have weak electrolyte. In other words, it conducts electricity weakly, all right? I don't mean every 7 days. I mean to a not strong degree. All right? All right, so now if you have another compound which is not soluble, this does not dissolve in water, then you would simply say this is not electrolyte. What? Does not dissolve? Okay, all right. Now I'm about to give you a table which is going to be a very important table. All right, so the second time I've said this semester. Oh, by the way, here's a silver compound which is soluble, and so it does make ions, right? Bunch of ions in solution. And so it does conduct electricity. It is an electrolyte. Conducts electricity, all right? Or it's an electrolyte. All right? Now, how are you going to know if something is soluble or not? How are you going to know something dissolves in water or not? And here is the key. All right, so we're going to use this table over and over and over again. I'm going to ask you to like it. We'll do one example here in a minute, but you must practice using this table. If you see, look at how this goes. Compounds containing the following ions are generally soluble, and compounds containing the following ions are generally insoluble. That's what this column here is, and here's the exceptions. Okay? So, if you have a compound with lithium in it, is it soluble or not? Yes, it is. Can you see that? No matter what it is. So, lithium chloride is going to be soluble. Lithium nitrate is going to be soluble. How do you spell lithium? Lithium, I don't know, nitride, sure, that'll be soluble, right? Why? Because it has lithium in it with no exceptions. Can you see that? Okay, what about sodium? Anything sodium. Sodium chloride. Oops. Na2, sodium sulfate. That's going to be soluble. Why? Because it's here with no exceptions. Okay? All right, now those are cations. Now look at these anions, nitrates. So if you see nitrate, it doesn't matter what what it's compounded with. It's going to be soluble because there are no exceptions. You see that? And the same with acetate. So silver nitrate is going to be soluble because it's a nitrate and there are no exceptions. Silver acetate, C2H3O2, is going to be soluble because it's an acetate and there are no exceptions. Okay, so you need to walk through this table and think about it like that. Right now, chlorides will usually be soluble, right? Chloride. However, when it's bonded with silver, mercury 1, or lead 2, the resulting compounds are insoluble. So, lead 2 iodide, that's lead 2 iodide, right? Because it's got 2 plus on it. Iodide's got 1. Lead 2 iodide is going to be insoluble, right? But potassium iodide is going to be soluble. right? Because it's not one of these exceptions, and also because it's up here. Okay, so that's how we're going to use this table. I'm not going to walk through each of these with you, but we should do some. I've shown you how to use the table, and now I'm going to ask you to look at table 4.1. It's on page 147. Very important table. You need it. Page 147. Likely we'll have a quiz on it tomorrow, and or whenever. Yeah, I don't know when you're watching this video, but likely we'll have a quiz on it, and I will probably give you this table the first time that we do a quiz, but not after that. Right? You need to know the table. You need to memorize it. You need to memorize it soon. So let's do an example when we're done with this section. I think that's all for this section. Yep. Let's do an example. So in each compound, let's see. Is each compound soluble or insoluble? All right. So first thing I'm going to do is I'm going to come here. I'm going to say lead. It's scary. I don't know. But I know chlorides are not, right? This is going to be lead 2 chloride, right? So I'm going to go back here, and I'm going to go chlorides. Oh, no, I'm wrong. I don't know what I said a moment ago, but let's pretend I said the right thing. Chlorides, right, are generally soluble except when they're bonded with these guys. You see that? So it's insoluble. So lead chloride is insoluble. So is each compound soluble or insoluble? Lead 2 chloride is insoluble. Okay? I'm going to lose these notes every time I switch back and forth. Copper 2 chloride, CuCl2. This is going to be soluble because it wasn't in my exceptions. I'm going to go back. I'm going to lose all these notes when I go back and forth. Okay, I'm going to come back and I'm going to have to pretend you can still see it. This is going to be gone when I come back. So here's my chloride, right? And copper is not an exception. So since copper is not here, so then copper 2 chloride is soluble. Okay? So, C. Remember A and B are still here in your mind? C. Copper 2 chloride is soluble. What about D? Barium sulfate. So we're going to do the same thing with barium sulfate. When I come back, this is all going to be gone. You pretend it's still there. Barium 2 sulfate. Where's sulfate? Okay. Oh, there's sulfate. Sulfate is right here. So sulfates are generally soluble, okay, except when sulfate pairs with strontium, barium, or silver or calcium. The resulting compound is insoluble. And so barium sulfate, according to this rule, is insoluble. Okay? So, barium sulfate is insoluble. Copper 2 chloride was soluble. Oops, that was B. Oh, I never did calcium. What? I never did calcium nitrate. All right, we got to go back up there. This was B. Did I do that twice? All right, calcium nitrate. So I come here and I say, nitrates are generally soluble, except, okay. So calcium nitrate, right? Calcium's always 2+ because it's in group 2. Nitrate's always -1 because it's always nitrate. So it looks like this is going to be soluble. All right. So I know I just said this. Lead 2 chloride is insoluble. Copper 2 chloride, yeah, is going to be soluble. Calcium nitrate, nitrate's no exceptions, always soluble. It's going to be soluble. And barium sulfate is going to be insoluble. All right, I hope that's helpful. You're going to need that table. You're an amazing person if this lecture alone makes that look easy. It's going to take some practice. Best wishes.